Hello, everybody. We're going to be working on Unit 12, which is the deep learning unit with part two, basically, to continue what we were doing in Unit 11 last week. We have some new topics to talk about here, including bias and variance, and then methods within deep learning we can use to mitigate those two factors, and then how we will implement all that with code. I'm going to switch over to our PowerPoint here and get us to some content slides. So once again, the agenda for the content, and let's dig in and get through it. All right, when we start working with data and we're using it to do modeling, and we've talked about these concepts before. So this is kind of deepening a little bit of that, but just to kind of refresh our memories on it. Um, when we're building machine learning models, we usually have some sort of data that we use to train our models, right? To make sure the models are working correctly. We try not to use, all of our data. So you can see me like moving the mouse here. Um, so we use a portion of it for training, and then we reserve a portion of it so that we can test the model to see if it's all set up correctly. Um, we also can take a portion of that data and then actually use it for validation. So, in other words, take a portion of that training data and reserve it for refining the model. So if you think back to the stuff we were talking about in the previous unit, where one of the things about deep learning is that we do have neural networks that have like recirculation points, or they refine themselves. So like the pathways that we follow, we might adjust the values based on the training. And so that data that gets recirculated would basically be the validation data. So this is like we throw our training data in there, we have our validation data, which helps to refine things. And then we finally have our testing data still to continue with that process. So it says here, they're giving an example. If you were, let's say, building a model that looks at the stock market, and they're using Intel stock, of course, is the example because it comes from Intel. And we wanted to predict what was going to happen in the following year. It would make a lot of sense to look at the previous year. So, and that's not unusual in financial forecasting, right? So we look at what happened, and they're using 2008 and 2009 here. So we would look at what actually happened in 2008 to train our model for what might happen in 2009. And so, therefore, 2008 becomes the training data, and 2009 is then the data that tests the model that we built in 2008. So, when we start with training data, we think of it often as the, quote unquote, initial data set. And once again, notice, how they use the word refine their rules, right? So this is the set of data that we use to kind of adjust things to move forward. We would basically keep adjusting parameters or values, once again, of the neural network to make it fit better, right? And they show the little breakdown here. Once again, the full data set is not used for training. In the previous approach, we used training data and testing data. And here, once again, we're using validation data to help refine the training before we test. That the point of it really is that, and they're showing it here in the third bullet, that we do have a need for quality and accurate, complete, and relevant data, right? And sometimes you do have data sets that have anomalous data, or data that doesn't quite fit, but it's still data, right? And so we have to consider all those pieces. And notice here it says the validation set is a set of data we did not use when training the model, and then we use it basically to assess how well the training is going as we're moving along. Now, when we make those adjustments, we call it tuning the parameters, or the inputs basically for our model on the various levels of the network. You could kind of compare it to, let's say, tuning a car motor. You can get the car to start, but maybe it's not tuned well, and little adjustments to, the air intake or the fuel distribution, or when the spark hits or whatever, makes it run better, right? um, and so that could be thought of as validation data. And then what would be the test would be driving it and it runs great. That would be, I think, a good example. Now, in terms of like what percentages to use, there are some thoughts on this. These are not rules, by the way. And these are things that people adjust, but there's kind of sort of a standard practice of like training data should be somewhere in the range of about 70% of your total data. Um, in the past, when we just went right to testing, we would use the remaining 30% then for testing. But in this scenario, they're looking at about 15% for doing the validation or adjusting the training. Now that 15% in some people's approaches would be incorporated into the 70%. Um, but that is highly subjective. It depends on the kind of data, the volume of data, et cetera. All right, so that um, and look at some of the terminology that they're using here. Is a test set is also known as the out of sample data or the test data. And these are things that we've talked about before, so I don't mean to keep regurgitating that, but this is the information in the slideshow that I'm trying to deliver to you. Once where it says trained on a particular data set, it's more likely to have more accuracy if the remaining data is really, really similar to the training data. I mean, it should work really, really well. And if we were to take the training and use all the data that was available, that might be good, but it might also cause a couple of issues as well. And notice that last bullet. A data set can never be comprehensive and can't teach everything that a model might encounter in the real world. And it says, therefore, a test data set containing unseen data points is used to evaluate the model's accuracy. So like in an ideal world when we're testing, that we would have a data set that might have some anomalies in it by intent. And if you think about real world scenarios, that kind of stuff happens, right? Like usually things work well and you have pretty consistent looking data, but every once in a while you get something that doesn't fit, right? Okay, so training data is used in model training, or it's used, basically it's the data used to fit the model. On the contrary, test data is used to evaluate the performance or accuracy of the model, right? And hopefully, right, it's used to make an unbiased evaluation of the final model and how that fits, and how the training data all fit together. The training data set is an initial data set that teaches the machine learning models to identify desired patterns or perform a certain task. And it says here, the testing data set is used to evaluate how effective the training was or how accurate the model is, right? And hopefully it is, right? And it all hinges on that data. So when we start adjusting our models, right? So in other words, that feedback loop that we were talking about the previous week. So we use that validation data set. Notice it says for frequent evaluation during the training phase. So it doesn't, so it wouldn't work, for example, like we do a bunch of training, then we validate it, then test it, right? Because at that point, the validation is really just like testing. There's kind of no point. The point of the validation data set is to tweak things as we go. Like, so for example, let's go back to that car analogy I was using. I start the car, I hear it's running rough, I adjust the carburetor or the fuel injection or whatever. And then I train it some more, right? And then I look at the data and go, oh, it needs a little bit more, right? So you might not make that adjustment right the first time. The point is to keep adjusting as you go during the training process. All right, and bullet number 2 is, although the model sees this data set occasionally, it doesn't learn from it. right? The validation set is also referred to as the development set or the dev set, right? So these are just alternate words that people use. And it protects the models from overfitting and underfitting. And we're going to talk about what those means, what those mean in a little more depth, just in a little bit here. Although validation data is separate from training data, data scientists might reserve a part of the training data for validation. And it makes sense, right? So we want to have that ability to tune the model. All right. So the big question at the top here, why do we need to split the data? And basically the answer is to prevent look ahead bias, overfitting, and underfitting. And here's what each one of those means. A look ahead bias is building a model based on data that is not supposed to be known, right? So we, if you can see what's coming, right, you can adjust for it, but that becomes a bias if you know what's coming. Overfitting is the process of designing a model that adapts so closely to historical data that becomes ineffective in the future. So if it gets weird data that it's never seen before, it might be overfitted to the training data and therefore become kind of ineffective. Underfitting is kind of the converse of that. That's designing a model that adapts so loosely to historical data. So it's not really tight that it becomes ineffective in the future. So it's not really giving us any value. Basically, it's way too loose. So, and that's just to explain the terminology of these things. As we start to, tune parameters, and of course, the way that we will do this is through Python code, most notably through the scikit learn library. And we've talked about some of these parameters in the past, so this is a little bit of review. But if you remember, when we were setting these up initially, we were choosing, what is the training size, what is the test size, for example. They do talk about, the fact that it's got 7 tunable parameters, and then they go into this whole discussion, and this is a very geeky programmer thing, by the way, where they discuss the differences between attributes and parameters, right? And, attributes are different than parameters are, and there's a link here, and I would encourage you to follow that link and read up on that. I do happen to have it open in a tab here on the other screen, so I can just very quickly pull it over, and then if you want to kind of read, so we'll just kind of look at this very, very briefly. The key difference between an attribute and a parameter is that an attribute is a variable of any type that is declared directly in a class, while a parameter is a variable defined by the function that receives a value when it's called. Now, when we run those scikit learn functions, right, and we're sending values to it, that's what we're doing, is we're tuning those variables. Those are like inputs to the function that control the function, right? And an attribute is basically a value that's already declared within another object in programming. So you're not really, well, it's not that you can't change it, but you're not typically going to adjust that, right? So that's kind of the point of that. So this is kind of like, once again, like programmer geeky stuff, but interesting nonetheless. So the point is, we will control the things that we can control, like in this sample code that you'll see here. All right. So it says, let's explore the important parameters of the train test split function. And notice that we can accept a few different kinds of inputs to this. So it's really meant to work with structured data, on the most fundamental level, a Python list. But we could also work with NumPy arrays, which are similar, or SciPy matrices, or pandas data frames. And we've worked with all of these so far, right? And they're just different numeric structure. So a list is just a collection of values. A NumPy array is similar. Matrix is basically a list of lists, or a list of lists of lists. You can go multiple dimensions on those. And then data frames, which are also multi-dimensional data from pandas. So the very first parameter of the function takes X and Y of the data set as an input, right? So like the parameters, or basically what data structure are you feeding in? You're going to drop that in there, right? And it can accept a bunch of different types. And notice here they start talking about the float. And it says a float should be between 0 and 1 and represent a proportion of the data set to include. So in other words, we will set a value for that. If int represents the absolute number of test samples, and none if the value is set to complement the training size. So if the training size is also none, then it will be set to 0.25 by default. And that's just something that you need to know. So they're going to set it to 25%. And that may or may not be what you want, obviously, right? And we're already talking about. Oops, sorry about that. And it looks like my PowerPoint just stopped midstream there, so I'm not really sure why that happened, but let's go ahead and bring it back up. That was very strange. And we were not on that slide. There must be some sort of like weirdness in the code there. Let's go back to slideshow mode and flip my screen here. I apologize for the fumbling. Let's see if we can just very quickly get back to where we were. All right. So this is where we were hitting on. So once again, the number should be between 0 and 1. Absolute number of samples is an issue as well. So if we look at like little code snippets here, and I'm not going to like bring up a coding engine and demonstrate it because we do have like our sample notebooks that we can pull from. They give an example, for example, with the train test split, where they set the test size to 0.33, and they also set a random state, right? Now, we always kind of throw in the number 42. That's kind of a Hitchhiker's Guide to the Galaxy joke or whatever, but it can be a different seed value as well. That's just a common one to use. Now let's take a look at overfitting and underfitting. So if you have high bias, so your data is really tight, right? You're underfitting. And if you have too much variance or too much, it's too loose, basically, then we're overfitting. So, and it says here, bias is related to the training set error, and it's also related to underfitting, most typically, right? So bias is related to underfitting your model. All right, so it gives us kind of a little breakdown of bias here, and it says, definition. Imagine you have a classifier model, and then you've trained the classifier on the train set and calculated the train set error. If the train set error is high, we can say the model has high bias. And if the train set error is low, then we can say it has low bias, right? So that's it. So in a nutshell, the high train error corresponds to high bias, right? The main reason between a high train set error is that our model is underfitting the training data. That's why high bias is also related to the underfitting, right? Now we're kind of looking at that here in the little animation. Variance is related to the test set error. So how big is the test set error compared to the train set error? And it is also related to overfitting. So let's kind of break that down. So variance, therefore, variance refers to the changes in the model when using different portions of the training data set. And it's basically the variability in the model prediction, how much the machine learning function can adjust depending on the given data set. Variance comes from highly complex models with a large number of features more typically, right? So like if you're dealing with a really complex equation or, that type of thing, the more features it has, the more nodes in the network, the more pathways, etc., more hidden layers. That's where the variance comes from, right? So models with a high bias will have low variance, and models with a high variance will have low bias. So the characteristic of a high variance model, there's noise in the data set, right? There's the potential towards overfitting. The models are complex. We were just saying that, right? And trying to put all the data points as close as possible, right? And in the real world, that doesn't always work that way. Now, one thing that we can do is we can address bias and variance with generative AI. So if we have GANs and VAEs that generate synthetic data representing basically data that's more diverse and balanced than the original training data. So in other words, we might have a like real data that is real somewhat tightly fitted, right? But we can generate synthetic data to kind of break out of that a little bit and train the model with a little bit more diverse data, right? And that's kind of the thinking. Incorporating the generated samples along with the original data can help mitigate bias by providing a more representative training set. And even though this is not a great example, this is like what I do sometimes in some of my classes, and I think I've done it in this class, for example, where I generated simulated Fitbit data, you know, because let's face it, the data that we were given maybe wasn't useful, or maybe we don't have a Fitbit to draw data from, or whatever. But having some real data and then mixing it with synthetic data, that can help us. So that's one technique. Um, all right. So once again, my PowerPoint quit on me. That's very strange. So that's twice in one session here. And what choice do I have here but just to simply relaunch it? And it keeps telling me I'm going back to slide 14. Maybe I should. Yeah, this is a little irritating, isn't it? All right. Well, at least we know where we were at. So I think we were right here. And maybe I should take this as a tip and not be in slideshow mode. Maybe that's what's failing on me. I'm not sure. Um, all right. All right. So it says here, by creating synthetic samples for the minority class and rebalancing the training set, GANs and VAEs can assist in handling those unbalanced data sets. The generative models can aid the model in learning a more balanced representation and lessen the bias towards the majority class by creating fresh examples of the class that's underrepresented, right? So I don't have a lot of data for this. Hey, but I generated some, so I can at least have my model work correctly with that data when it comes into the mix. I mean that, and if you think back, we have talked about that concept also. GANs and VAEs can be trained to learn a condensed representation of the data, getting the key aspects of it basically while minimizing noise and unimportant data. This can help deep learning models focus on the most informative features and improve generalization by encouraging generative models to supply samples that match this representation. All right. Now, we've also talked about the adversarial training in a GAN, right? And here it says by exposing deep learning models to adversarial cases during training, adversarial training with GANs can improve the robustness of those models, right? And if you remember that whole process, right? Like you generate synthetic information and then you run the adversarial portion of it to basically try to prove that it's fake, right? So you just generated fake data and then you're trying to prove that it's fake. And what you're really trying to do is make it so the synthetic data isn't tripping that portion of it to indicate that it's fake, right? Remember that when we've talked about that. So, model can be trained to withstand adversarial attacks, making it more resistant to changes and disturbances in the input data. So this makes the model stronger, basically, by testing it to see if the data it's generating is fake. All right. And they have a little thing here kind of showing that process, right? Right. And it goes into the model. We extract the information. We poison the evaluation, and then we try to like work around it and deceive it. And then if it can pick up on the fact that we're trying to deceive it, then it's usually a stronger model. All right. I think this animation here is just an animation, but it shows the curve forming the data. So the model, I mean, clearly makes some sort of a shape, right? So overfitting and low bias and high variance, right? So, all right, so this is kind of the point of this. One is kind of giving you the general shape of the data, and the other one, like the original one, was drawing like a squiggly line, right? And notice the progression here, and we'll just kind of let it draw. So here's the original equation, right? Then we have this like jaggedy line, that's overfitting, right? Low bias and high variance, right? It doesn't make a smooth line at all. It's just a crazy path, right? Then we do this, which is underfitting. There's a lot of bias and no variance, right? It's a straight line. And then we draw another shape that's a good fit. There's low bias and low variance. So we're trying to balance those two things. So, you know, notice here it says when the size of the training data set is small, the network tries to learn from the small data set and will tend to have greater control over the data set and will satisfy all the data points exactly, right? So the network is trying to memorize every data point, failing to capture the general trend from the data set. So this is overfitting, and that would be the jaggedy line approach, right? All right. So the causes of overfitting in a neural network, the model tries to make predictions on noisy data. So overfitting also occurs when the model tries to make predictions on data that is very noisy, which is caused due to an overly complex model having too many parameters. So due to this, the overfitted model is inaccurate as the trend does not reflect the reality in the present data, right? So that is certainly problematic, and they're showing here, you know, what the main signal is and the noisy data, you know, all those data points kind of basically all over the place. Another cause of overfitting is model complexity, right? So when the neural network has a lot of layers, right, and we're, you know, thinking of the hidden layers in between input and output predominantly, the complexity of the neural network increases. Now look at all those possible pathways data can flow through, right? When we don't feed a lot of data to this huge network with many layers, the neural network starts overfitting. So, and notice if we don't feed a lot of data to it, right? So it's a big network, complex network. We barely have any data. All right, so that's going to cause overfitting just because of the lack of data. Therefore, a very large neural network does not necessarily mean good performance. And especially if you don't have a large data set. I mean, that's the implication here. Right, moving on to the next slide. All right, so how do we mitigate overfitting in a neural network? Well, data augmentation, right? Adding synthetic data to our data set, or generating synthetic data in areas where we are lacking data, right? Regularization techniques, the dropout layers, right? So maybe remove some stuff, right? Batch normalization is an issue, or early stopping. Those are all ways to kind of deal with it, right? And this one, and I think early stopping is kind of a weird one, right? It's like, all right, well, that made it data model is good enough. So we'll just stop here, right? And I think that's kind of an interesting one. So, all right. So now we're going to go into these a little bit one by one so we can kind of break down what they mean. So let's start with regularization and what that means. Regularization in a neural network, and kind of like just taking a look at like what underfitting and overfitting look like. So this is not too dissimilar from the graphic we were looking at before. The data points, right, generally kind of indicate a curved shape here, right? Overfitting is where we try to follow each data point, you know, and we get this like jagged, uncontrolled looking line. And then we have the underfitting of the data is like, yeah, it's just like this, you know, just it's just, you know, and you know what, it doesn't really address some of these data points, right? Where there is kind of a downward trend here and then an upward trend. It's not necessarily flat like that. So it says, as we move towards the right in this image, our model tries to learn too well with the details and the noise from the training data, which ultimately results in poor performance on unseen data, right? Because you throw a weird data point at it. Is it going to follow that line? Probably not, right? So, in other words, while going towards the right, the complexity of the model increases such that the training error reduces, but the testing error doesn't. So more complexity, the more the chances are of it getting overfitted. So and this is definitely a concern. More complexity. So we overcome this with regularization. Um, and there is a cost function basically of a neural network. And here's the formula basically for doing that. And it's a measure of how good the neural network did with respect to its giving training sample and the expected output. So it also depends on the variables such as weights and biases. A cost function is a single value, not a vector, because it rates how good the neural network did as a whole, right? So we're not looking at little aspects of it, we're looking at the overall performance. All right, so how does it help? Well, weight regularization penalizes the network's large weights and forces optimization algorithm to reduce the larger weight values to smaller weights. And this leads basically to stability of the network and presents good performance. And it says in this technique, the network configuration remains unchanged since it only modifies the value of the weights, right? So the weights would be, the values for traveling over certain parts of the network. You can see like that graphic that they have there, the overfitting, where they're trying to make the function line include those red X's no matter what, right? And they're going out of their way to make it happen. That's overfitting. All right. So what does penalization of the weight matrix mean exactly? All right. Well, what it means is that if you look at this network diagram, right? So we have some inputs and they're moving on to one of the layers. And then as we travel the pathway, so like if we're going from, let's say, from example, input one to node one, right? The weight is represented as a 1, 1. So W11 is 4, right? And really what we're forming here is a matrix. Like we can see the pathways in the diagram, but in terms of values, those fall into a matrix, right? Where you're basically taking every input, mapping it to each node and what those values are. The sub numbers represent the pathways basically. And and this is the weight matrix. So in other words, there's values for traveling any given pathway. Um, Sometimes when people draw these, they also just attach the values to the pathway itself because that's really what's happening. So keep that in your head as you're examining this. Now, the cost function works on this matrix that forms, right? And they use the lambda, right? And lambda is basically the regularization factor in this, right? So they, and that's represented by this Greek letter lambda right here. And it can be calculated, right? Because there's weights of the matrix or the pathways of the matrix or the network, and we're looking for that regularization factor, basically. All right. So by changing the value of lambda, we can control the overfitting and underfitting of the network. If the lambda is very low, then the cost function is reduced quickly and the neural network underfits, right? So example, if we set lambda to like 0.001, right? If it's set really high, then the cost function doesn't reduce and then it starts to overfit. So for example, if the lambda is set to 1, so it doesn't take a genius to figure out, you got to set it somewhere in between. And so let's kind of like take a look at this. So overfitting creates the crazy pathway, right? So if we're really close to 0, right, then most of the weights in the weight matrix become 0, and in turn the neurons get deactivated. So in other words, we're just ignoring a bunch of pathways. We're just saying these are the pathways to follow and make it really, really tight, right? And of course, underfitting is going to be the converse of that, right? So they go through the mathematical explanation of it. So L1 regularization is the preferred choice when having a high number of features, as it provides sparse solutions And then even when we obtain the computational advantage, because it features zero co, so in other words, things that where the pathways are set to zero, they're just going to be avoided, right? And that's really kind of the point. By setting that too low, you're just saying, okay, well, we're just, you know what, that's not the path we want to take, right? You're just not even making it a possibility anymore. So the deep learning model that uses L1 regularization technique is also called lasso regression. And why? Because of the weird shapes it makes in the curvatures, basically. L2 regularization can deal with multicollinearity, independent variables that are highly correlated. So this is like um, highly correlated linear equations, basically. And it deals with it through constricting the coefficient and keeping all the variables. L2 regression can be used to estimate the significance of the predictors based on it, and that can penalize insignificant predictors, right? So ones that don't have a lot of value basically get hit, so in other words, they don't get used. A regression model that uses L2 regularization techniques is called ridge regression, by the way. So now we're going to take a look at how do we implement this using the keras library. And they have a little example of code here once again. And so once you get TensorFlow and keras imported, and I do want to be mindful, that some of us have been having issues getting TensorFlow installed. And in some cases, the trick was downgrading the version of Python. So just keep that in your head. But if you do get stuck with that, please reach out to me and I can help you through it. It's also something that's good to share in class so that everybody is aware of it. All right, so if you look here at some of the code, right, so you have your imports, and then you look at your different layers, right? We can look at the regularizers, and you'll notice that they actually declare L1 underscore L2, right, where you declare it kind of different values. And we also have regularizers basically for the kernel, the bias, and the activity. And so, and as is implied, the regularizer to apply the penalty on the layer's kernel, on the layer's bias, and on the layer's output, right? And so this deals with all three of those aspects. The available regularizer function, keras dense function, is a little bit different here. That's a regularizer that applies L1 regularization, a penalty to it, basically. And it's computed as a loss. So, they show you the equation here, but it may be passed to a layer as a string identifier. So you can just basically set it up, right? And then pass it as a value, right, to a different function. So you can pass it to the dense function, and actually kind of build it right into the parameter. The L2 class, that applies an L2 regularization penalty, shows you the equation once again, and that's also passed in much the same way, right? So you can pass it as a parameter. So in other words, the spot in the code that you need to tweak. If we use the combo L1, L2 function, that it applies both the L1 and the L2, right? So it may be preferred. And it works basically with the given regularization factors, right? So both the equations are incorporated then. All right, so let's now take a look at the role of generative AI in regularization and how variational autoencoders, the VAEs, can be used to regularize the learning process and prevent overfitting. So the VAEs are generative AI models that can help with regularization. They consist of an encoder network and a decoder network. And I don't know if you guys recall that from our earlier lectures or not, but here it is again. So we have this thing called latent space regularization. So VAEs regularize, that's a hard one to say, latent spaces which compress input data It promotes latent space distributions like multivariate Gaussian, for example. Um, this constraint stops the model from over-focusing on specific occurrences and in training data and promotes more general representations. We can also use generative sampling, and VAE is basically regularize learning through generative sampling, and the decoder network generates samples from the learned latent space distribution. After comparing the values of these samples to the original input, the model modifies its parameters to minimize reconstruction loss. The model learns increasingly robust representations that capture the data structure with this generative sampling. The regularization effect basically leads VAE to prevent overfitting, right? To not have those crazy lines, right? They encourage more generalizable representations by urging the model to capture the fundamental data properties rather than memorizing individual examples. Now, you guys think back when we started talking about a memory, right? Where we had feed forward networks had no memory, and then we had the ones that would recirculate information that had memory. So we're trying to adjust to that basically. This improves unseen performance and reduces overfitting. Places where this is used is image generation and text generation. Now we're going to look at data augmentation and how this is going to help reduce bias and variance. So how do you overcome the small data set problem, right? So we talked about this before. So if you have a complex network, but you have a small data set, and it says one of the best strategies to avoid overfitting is to increase the size of the training data set. When the training data size is small, the network tends to have greater control over the data, right? But in real world scenarios, gathering large amounts of data is tedious and time consuming, and the collection of data might not be viable, right? So in other words, how do you test when you can't get access to the data? Right? So how do you do that? Right? Data augmentation basically increases the number of samples. So it provides techniques to increase the size of existing training data without any external addition. So this is, where our Gen AI comes in handy. The training data consists of images, image augmentation techniques like rotation, horizontal, vertical flipping, translation, increasing or decreasing the brightness, adding noise, cutouts, and those can all be applied to existing training images to increase the number of images. So in other words, they can take that same butterfly, adjust it a few different ways, and now instead of one data point, you have 6 or 10 or 20, right? All based on that one original butterfly. And that helps to generate the data that we need to train the model. Model performance after data augmentation, right? So the blue line shows the training accuracy, and then the orange line shows the test accuracy. So it says performance before data augmentation, not so great, right? It's pretty low. It doesn't really match what we're seeing, but after data augmentation, it improves. It can be seen that both the train and test accuracy increases after data augmentation, right? I don't know why they put them in this order, but this is the after and this is the before. To my mind, it should be flipped, but whatever. Therefore, it can be concluded that with more data through data augmentation, the variance decreases, right? So the difference between the blue line and the orange line is smaller, right? Which means the model is basically fitting better. All right. So now we're going to flip back to using TensorFlow again to do some of the augmentation. So let's look at some example here. This is the image generating function from the TensorFlow library. It has 22 tunable parameters. If you thought 7 was a lot, this is a whole lot more. And you can see some of the things that they have here as parameters. I mean, you can just kind of read them and figure that out. But, we talked about like taking the butterfly image and flipping it horizontally or vertically or rotating it. You can see all that stuff is kind of built in here. So it does have a whole bunch of tunable parameters, and some of them you adjust and some of them you don't. It really kind of depends. Image augmentation techniques with the keras image data generator can do the following, right? We just talked about these rotation, shifts, flips, brightness, zoom levels, all those different things, and all with the purpose of creating additional data points that we don't have. All right. What are dropout layers? So regularization techniques prevent the model from overfitting by modifying the cost function. Dropout, however, prevents overfitting by modifying the network itself. After each iteration, different sets of neurons are deactivated, and this results in a different set of results. So I'm going to run the little animation here so you can see what I'm talking about. So like you might, as you're running it, maybe get to the point where you're eliminating certain neurons because that's the better fit, so it's not necessarily that the whole layer will drop out, but on this layer, certain nodes will drop out. Notice there's a p-value here, which is designed to, okay, we're going to drop half of them, right? Because we go from 0 to 1. So that's the percentage, basically. There's also early stopping. If you remember, we talked about that. While training a neural network using an optimization algorithm like gradient descent, which we were talking about previously as well, the model parameters or the weights basically are updated to reduce the training error, right? So, and what they're attempting to show here, right, is as we keep going through the training, right, the training error drops, but the testing error starts to rise. So maybe we stop here, right, before it gets out of control, right? It's starting to diverge at this point, like a little bit moving away from that line. And so that would be the point of, stopping early or early termination. So it says at the end of each forward propagation, the network parameters are updated to reduce the error in the next iteration, right? So that's done with intent. The graph indicates the point after which a parameter network begins to overfit, and the parameters at the point of early termination are the best fit for the model. So to decrease the test error beyond the point of early termination can be done by decreasing the learning rate. So that would be applying a learning rate scheduler algorithm. That would be the recommendation, or applying a different optimization algorithm. So change the algorithm, right? Or applying L1 and L2 regularization, right? So on both levels, right? So if we're going to implement early stopping with code in TensorFlow, it's going to look a little bit like this. So this is what we call early stopping callback. And notice the name of the function is called early stopping, right? And notice the parameters that are available here. And it says, assuming the goal of training is to minimize the loss. With this, the metric to be monitored would be loss, and the mode would be to minimize it, right? And see, these are, optimization questions that you have to ask in advance. Usually the mathematicians are probably worried about this one, in particular. The model fit training loop will check at the end of every epoch, right? So every iteration, if you will, whether the loss is no longer decreasing. So every time we're moving to see that loss isn't like, getting smaller. All right, let's start to look at some of the parameters here. So in this one, the monitor is the quantity to be monitored. So like, what is the thing that we're looking at? So we just talked about this. In this case, the loss of value, right? And that's the one that's said here. So an example might be accuracy or F1 score or test loss. might be some of the types of terms you're looking at here. The minimum delta is the minimum change in the monitored quality to qualify as an improvement. So, for example, an absolute change of less than the minimum delta will count as no improvement. And for those of you that aren't mathletes, whatever, delta is basically the rate of change. And here we're setting the minimum change amount, is what that really refers to. The other ones that we have here that we're looking at are one of auto, min, or max. And that would be basically our mode. And in the min mode, the training will stop when the quantity monitor has stopped decreasing. In max mode, it will stop when it has stopped increasing. And auto will figure it out automatically. Are you decreasing or increase? And so often, a lot of people leave it in auto mode because it becomes kind of self-explanatory. There are situations though where you do have to set it to max or min. These are our key takeaways here, folks. But this kind of wraps up the lecture portion. And for those of you that are in my class, I'm just going to take a really quick look at our assignment here on this. We do have some dependency files here. It's just basically one notebook that's set up. And basically the assignment for this week will be to figure out the bias and variance for a learning rate controlled model by changing the L1 and 2 regularization rates and the dropout rates. There are examples in the notebooks, and what they want you to do is basically to locate these, L1 and L2 rates, change them to the following values, and then summarize what you see. For the sake of making sure that it's working correctly, here is the expected output you should receive, right? I do want you to generate your own output though. So just be mindful of that, but at least you have a reference here to look at. And you can take that image and zoom in on it if that's helpful. So the one is to do the L1 and L2 regularization. And the other part is to adjust the dropout rates and notice the different values that they're using here. And once again, we have an expected output that you should be getting. And they show you the code here as well. So you can just find that in the notebook, tweak it, try the different values, and then summarize what you see, right? And what I'd like to get a little verbal feedback from you on what you're seeing in it and what you're getting out of it and how that applies to the concepts that we just learned. Standard technique for turning stuff in, screenshots of the output in the code. Please submit your code file as well. Using Gen AI to help you is perfectly acceptable. Just let me know which AI, what prompts you used, and what it gave you or what it helped you with. All right, folks, this video will end here, and I will get it published as quickly as possible in lieu of tonight's class on July 22nd, 2025.